Greetings everyone. Welcome to Side A, Side B. In this video, prove the Angle-Angle-Angle Theorem of similarity in geometry. The overall plan: develop a line of thought supported by definitions, postulates, corollaries, and theorems. So what's in our toolbox? How about straight up algebra and geometry? Coming up shortly, we'll see the usefulness of the CP-CTC theorem, which we just proved, by proving all the unknown parts of triangles are congruent by first proving that triangles are congruent with the givens. On that note, first, a discussion covering all the angles of similar triangles. When we talk about two similar triangles, notice triangle Y looks like a smaller version of triangle X, whereas Z is for sure a triangle. However, we'll bet $100 Z is not a smaller version of X. It simply looks out of proportion. We can't be that sure for Y though. Wish it were that simple, because we can't be 100% sure without a proof. Aw, but it looks the same. We feel the same way. It would be easier if we just accepted it looks the same. But fortunately, there's a mathematical approach to show the triangles are similar. One approach is using angle-angle-angle similarity. And if you can say that, you're halfway there. Which means, if two triangles are similar, then all their corresponding angles equal each other. We should find the angles in the yellow circle are the same. The angles in the second yellow circle should equal each other. The angles in the third yellow circle should equal each other, which means X and Y are similar because all their angles match exactly. What does every triangle in Euclidean geometry have in common? Their angle sum equals 180 degrees. So, suppose we do this. Measure two angles. We find the angles equal the following values. Then it's possible to solve for X. Is that not the case for every single sum of a triangle? For every angle sum, there's going to be one answer if the equation is set up this way. But that's actually good news, because as it turns out, if we know the values of just two angles of a triangle, which correspond with two other angles of another triangle, if we have these conditions, then we can solve for any missing value X. Then we only need two angles to prove similarity. Consequently, the angle-angle similarity, which is actually easier to say, approach to prove two triangles are similar is what's most popular to use, and that seems very straightforward. Pardon the pun. However, the angle-angle-angle theorem considers all, as it were, covering all the angles. Let's begin. Welcome back. To further clarify the idea of similarity, two conditions are naturally met. The first is what we discussed already, the triple angle criteria for similarity. All corresponding angles are equal. The second one is all corresponding sides are proportional. Put differently, we should be able to find a scalar value that can scale up or down one of the triangles so that we could place it on top of the other triangle in such a way they would coincide with each other. That being said, upon meeting both of those conditions is what it means for two triangles to be similar. Enough chitter-chatter. Let's get into it, ladies and gentlemen. The theorem states, if, for two triangles, all their corresponding angles are equal, then all their sides are proportional. For the following two triangles, we are given angle A equals angle R. The same can be said for the other corresponding angles. Then, we want to prove the triangles are similar. Since we are given the blue box, we need to prove the yellow arrow. Does that sound good? If it does, then essentially we want to prove the following triple equality. RP over AB equals PQ over BC equals RQ over AC. Then consider the two triangles RPQ and AXY, where by construction the line RP equals the line AX and the line RQ equals the line AY. Also the angle A equals the angle R, such that triangle RPQ is congruent with triangle AXY by the side-angle-side postulate, which we don't have to prove. Nice. Next slide, please. Then by the CP-CTC theorem, I wish there was a shorter form for that, but that is the short form, which we just proved in our last video, angle P equals angle X and angle Q equals angle Y. In spite of the name, that's the usefulness of the theorem, proving all the unknown parts of a triangle are equal to each other by first proving that triangles are congruent with the givens. Hence, if angle P equals angle X and angle P equals angle B, then by the transitive property, angle X must equal angle B. Now we refer to the definition of a transversal in geometry, which states a transversal is a line that intersects two or more other lines at distinct points. These lines being intersected can be parallel or non-parallel. The transversal naturally creates various angle relationships when it intersects the other lines, such as corresponding angles, alternate interior angles, and alternate exterior angles. The one we're concerned with, corresponding angles, which are angles that occupy the same relative position at each intersection, in this case, the upper right. Moreover, if the lines being intersected by the transversal are parallel, then a special relationship exists between these angles, which is corresponding angles will equal each other. If we extend the lines XY, BC, and AB with the perforated lines, we see this is the case. We have a transversal AB intersects line XY and line BC, and we have a pair of corresponding angles X and B that equal each other, which means the line XY is parallel with the line BC. Make sense? That's very nice, because now that we've established all of the above, and those lines are parallel, we can refer to Thales' theorem of proportionality, which we proved already, which is AX over XB equals AY over YC. Now we can refer to the corollaries 1, 2, and 3 of the same theorem to show the triple equality in the white holds true, which means triangle ABC is similar to triangle RPQ. We are done. To summarize, by using algebra and definitions of geometry, like the definition of a parallelogram, we can prove the corollaries, which will establish. Imagine a line YK parallel with the line AB, which will essentially consider all the sides of the triangle. It follows. We'll show all three sides are proportional, making the white box hold true. However, if that still doesn't make any sense, then we highly recommend to watch the Thales theorem video, also the corollary proof videos, and then come back. To conclude, what do you think? Did that cover all the angles? Except an exit, which we'll cover right now. Until next video, ladies and gentlemen.